Concept 16b, finding zeros and graphing polynomial functions. So let's start with some vocab definitions and formulas. We're going to talk about the end behavior of graphs in this section. That is where the ends of the graph go. So are they heading down and to the left or up and to the right? On the left, are they going up, or on the right, are they heading down? So that is end behavior. We're also going to talk more about zeros of a function, like we did in 16a. These are the values that you get for x when you set a polynomial equal to 0 and solve. Because we're talking about graphing in this section, we're going to talk about the turning points of functions. This is a place where a graph switches from increasing to decreasing, or vice versa, meaning decreasing to increasing. The graph turns. The number of turning points is one less than the number of real zeros that a function has. And then finally, the last concept we'll talk about is multiplicity. This is when a zero comes from a factor that has a power other than 1. So first let's talk about an end behavior of polynomial functions. So a function's graph, it's the behavior of it as it just approaches as x gets bigger or as x gets smaller. And so we have just 4 random polynomial graphs here. And notice that this graph on the upper left has end behavior that is, as x gets bigger, it's going down. And then as x is getting smaller, and then as x is getting bigger, the end of that graph is going up. You will have a situation if the degree of your polynomial, that means the highest exponent term, whoops, I'm sorry, not 3, I meant to write, is odd. So like 3. So you have a cubic function, or maybe a function that's to the 5th power. Also, the graph will be down on the left and up on the right if the leading coefficient, that means the number in front of the biggest variable exponent term, is positive. Now, if your degree is odd and the leading coefficient is negative, then you will have end behavior that is up on the left and down on the right. So you can think of it kind of like a positive slope of a line and a negative slope. So positive leading coefficient, negative leading coefficient. If your degree is even, like you have a function to the 2nd or to the 4th or the 6th power, and the leading coefficient is positive, your end behavior will be up on the left and up on the right, just like this example graph is doing. And then if your degree is even, but the leading coefficient is negative, you'll have end behavior that is down on the left and down on the right. Now, because polynomials have lots of things going on in their graphs, I'm going to rewrite this. I was reading that so you can see it. There. Then it's good for us to first just look at the equation and draw some, general thoughts about what the graph is going to do. And so that's what we do first. We look at end behavior. And to figure out end behavior, we need to know the degree, which we covered in concept 14, and then we need to know how to pick out the leading coefficient, which we also covered. So let's look at the first 2 examples and simply describe the end behavior. So we notice that our function is in standard form because our exponents are in descending order. Our degree, it's the highest exponent, so our degree is 4. And now we're going to make note that that is even. Our leading coefficient, I'm just going to write that as LC, is negative 5. And we make a note that it is negative. So if you look back on your notes, you can see that that end behavior is going to be down on the left and down on the right. So if we did a quick sketch of a graph, and we'll just do the ends, it's going to look something like that. Now the next function is not in standard form. So let's rewrite it. I'm going to put my negative 4x to the 5th term first, and then my negative 12x to the 4th, negative 18x squared minus 2x plus 11. So my degree is 5, and I'm just making note that it's an odd degree. The leading coefficient is negative again, it's negative 4, and I note that it is negative. So that means my end behavior, if you look at your notes, is going to be like a negative slope of a line, up on the left and down on the right. If we were to sketch that, we could just write arrows that are up on the left and down on the right. Now let's write a polynomial function whose graph has the same end behavior as the graph on the right. So we look and our end behavior is down on the left and up on the right. So it's down and up. And if you look at your chart, you can see that we need a function that has a degree that is odd. And the leading coefficient needs to be positive. So let's just say y equals a positive number, let's just say positive 4, and then a variable x, and then an odd degree, how about 3? So that graph would have the same end behavior as the graph on the right. We're going to move into graphing polynomial functions now. To graph polynomials, we're going to factor them, which we covered in section 16a, to find the zeros. That's where they cross the x-axis. These will be the points called the x-intercepts. Now, to figure out how many turning points a graph has, because sometimes these polynomials do, like the example you can see on my slide, you look at its zeros. So for n distinct zeros, the graph has exactly n minus 1 turning points. So we could work backwards with this graph. This graph has 2 turning points, and that's where, it is increasing and now it switches and becomes decreasing. Here it's decreasing and then it switches and becomes increasing. So since it has 2 turning points, that means its degree is 1 higher than that. So it has to be a degree of 3. Now let's find the zeros of the polynomial and graph this. So first of all, our leading coefficient is 3, and let's just make a note that it is positive. Our degree is also 3, and that is odd. So let's just talk about end behavior, and we'll sketch it on the graph. So odd positive will be down on the left and up on the right. Now for the zeros, we're going to set this function equal to 0. We'll divide by 3. X cubed equals 0. And then we ask ourselves, what number can we multiply by itself 3 times to give us 0, and that has to be 0. So that is where it's crossing the x-axis. So that means the turning points, since it only has 1 0, which is the point 0, 0, or it only has 1 x-intercept, to find the turning points, we do 1 minus 1. So it is not going to have any turning points. It's going to do something like this. It's just going to do a little jog in the middle. Now with this function, let's find the zeros and graph it as well. So first let's talk about the leading coefficient. It's positive 1, and it is positive. We'll make note. The degree is 3, which is odd. So same end behavior as before, down on the left and up on the right. Now to find the zeros, let's factor. Notice that there are 4 terms. So let's factor by grouping. Let's just divide that function in half. We'll factor out an x squared and be left with x plus 5, and then a negative 4, be left with x plus 5. Now your common is x plus 5, so we can factor that out front, which is essentially dividing it out. And what you'll have left is x squared minus 4. Just keep factoring. So x plus 5, and then this is the difference of two squares. It's x and 2 that's being squared. And that is equal to 0. Now if we set these each equal to 0, so on this first one, we know that we'll subtract 5, so our first 0 will be at negative 5. Our next one, we set that equal to 0 and then subtract 2 over, will be at negative 2, and then this one will be at positive 2. So we can put those points on the graph. So on your x-axis, graph negative 5 and negative 2 and positive 2. And so this graph, since it starts down on the left, it's going to go up and then come back around and go back around one more time. Since it has 3 zeros, that means it will make 2 turning points. So here and there. Another concept that I mentioned in the definition section was multiplicity. This is a label that we give the zeros of our function, and that's when a zero comes from a factor other than 1. So if you were to think of this function set equal to 0, the zeros are going to be negative 1 and positive 3. But because that negative 1 comes from a factor that has a power other than 1, we say that it has a multiplicity of 2. And then 3, since its factor has a power of 1, it has a multiplicity of 1. So in the next example, if we were to set x to the third equal to 0 and solve, then this 0 would have a multiplicity of 3. And then if we set x plus 2 equal to 0, this just has a multiplicity of 1. So you look at the power that the factor comes from, and if it's other than 1, you say it has a multiplicity of whatever that power is. So let's do this last graphing problem. First of all, let's look at the leading coefficient, which is 5, and it is positive. The degree is 6, which is even. So we're going to have n behavior, that is up and up. To find the zeros of the function, let's set it equal to 0 and factor. Remember to look for a greatest common factor. I see that we can factor at a 5x to the 4th. And we'll be left with x squared minus 4. Notice that x squared minus 4 is the difference of squares. It can be factored as x plus 2 times x minus 2. And then we can set each of those equal to 0 and solve. So that will be 0. This will be negative 2. Let's try that again. And x minus 2 equals 0. This will be 2. So we can plot those at 0, negative 2, and 2. We can see that this has a multiplicity of 4. I'm just going to write it in red. But this just has a multiplicity of 1, and the same for that one. So the graph is going to look like this. Since we have 3 zeros, we will have 3 places where the graph crosses the x-axis at, again, negative 2, 0, and 2. And so that's how we sketch the graph of that polynomial.